we go. Here we go. Now we're recording. All right. Okay, so I'll just go over some of the mixed Nash equilibrium things, just a few random thoughts about it, and some random things about Nash's theorem and its proof. And we'll answer your questions at the end, hopefully. All right. So let me start by reminding you about the support characterization. Okay, so support characterization, it gives you something about the best response function, right? So the idea is that to be in the best response function. So if you have a mixed strategy, right, so given a mixed strategy of the other players, a strategy pure mixed for player I is in the best response function. Okay, so for a strategy to be in the best response function, it means that any pure strategy with positive probability in Xi must be the maximum. Utility among all pure strategies. Okay. And so support characterization says that given any strategy set from the other players, your strategy is in the best response function if and only if any pure strategy with positive probability must be the maximum utility among all pure strategies. So there is a relation between the mixed strategies and the pure strategies, right? So the mixed strategies do depend on having the pure strategies, the utility for the pure strategies. Okay. All right. So, so the idea is then to figure out whether or not a mixed strategy is in the best response, you only need to calculate the pure strategies, the utility for the pure strategies only. Okay, right. But so then what I want to say is, what is the relationship between the utility for those pure strategies and these mixed strategies? Okay, so what is the relationship between a pure best response versus just any mixed strategy? Right? It seems that anytime we talk about mixed strategies, we talk about the pure strategies as well, right? So, so what is the relationship between a pure best response versus any mixed strategy, right? Right. So we have, so the support characterization gives you some idea about this, but let's just give you an example of how this works. Okay, all right. Suppose I have x minus I that is fixed. And for player I, we have, let's say, four pure strategies. Let's say they are A, B, C, and D. Okay, so we have the mixed strategies for the other players that is fixed. And for player I, there are 4 pure strategies, A, B, and C, and D. And let's say their utility. So let's say the utility of player I for A, B, and C, A, B, C, and D. Let's say, oh, just make a number. So it's 10, 7, 5, and then maybe I'll do another 10. Okay, so 10, 7, 5, and 10. Okay, all right. All right, so at this point, we just say, well, A and D would be the best possible pure strategies for player I. Okay, and they have utility 10. Okay, all right. But then what can you say about the mixed strategies? Right? So if you look at the mixed strategies of player I, what is a maximum for that? Okay. Right, so for a mixed strategy, oops. So for a mixed strategy for player I, what is its maximum utility? Okay. All right. Right. Okay, so then here's where you say, well, suppose X I is, say, let's say P1, P2, P3, P4. Right, so it's P1, P2, P3, P4. That is the strategy that we're playing for player I. The utility for this one is then, you can probably prove this, 10P1 plus 7P2 plus 5P3 plus 10P4. So basically that is the combination of these utilities, right? So 10 times the probability of playing A plus 7 times probability of playing playing B, etc. Oh no, we don't have to prove this. This is a definition of utility. Okay, so that is the definition of utility. Okay. All right. And if you do some math involved, right, so this one has to, so we're looking for the utility here. P1, P2, P3, P4, they should add up to 1. So essentially, we are averaging the 4 utilities in some way. Okay. So we are averaging, not I guess, weighted average. We're doing a weighted average of the pure strategies. Okay, so we're doing a weighted average of the pure strategies. Okay. Okay. So it really can't get higher than 10, right? So this utility cannot be higher than 10. Right? So if you distribute a probability over the 4 strategies, we know that the highest possible pure strategy is 10, and we're just doing the probability distribution over the 4 possible strategies here. So we cannot get anything that is higher than 10 in this case. Okay. Okay. And not only that, the only way to get 10 is if we remove the P2 and P3. Right? So those two has to be 0. Right? So if any of these weighted average goes toward the second B and C, then we will never get 10. Okay, so this is achieved. This 10 is achieved when we spread among A and D. only. Okay, so this is only 10 when we spread among A and D only, right? Because they have the highest possible pure utility for a pure strategy. We're averaging 10 and 10. So however we do the weighted average, it's going to be 10 as well. Okay. All right. Okay. So what this means is that in the best response function, we will include A and we'll include D. But we'll also include any of these, what we call the convex combination of A and D, right? So any of the ways we can average A and D, that would be in the best response. Okay, so any ways we can say distribute 1 to P1 to P4, so 50-50, 1/3, 2/3, any way of distributing them, that will give me something in the best response. Okay, all right, so our best response function would return anything, any distribution with only only P1 and P4. That is at least 0. Okay. Right. We will not have other things that are in the best response function. Okay, so that's the thing about the mixed best response function. The mixed best response function is essentially just doing the convex combination of the best response function for the pure strategies. Okay, and that is pretty much what we are saying for the support characterization. Right? So any pure strategy with positive probability must be in the maximum utility among all the pure strategies. Okay, all right. So I'll just write that down as a note. We can think of the best response as anything. I guess any convex combination of the pure strategies with maximum utility. Okay, so we can think of the best response as any convex combination of the pure strategies with maximum utility. Okay, so think of all the pure strategies that are maximum, take any of the convex combinations between them, that would be in the best response. Okay, all right, good. Any questions so far? Okay. All right. Okay, so hopefully that is clear. All right. So now we can talk about the idea of the proof behind Nash's theorem. Right, so let's look at, I can go to a new page. All right, so Nash's theorem. Okay. All right. So for Nash's theorem, the statement of the theorem is pretty simple. So any strategic gain with finitely many players and strategies, players and strategies, any strategic game with finitely many players and strategies must have a, well, let's say mix, but it could be pure mix Nash equilibrium. Okay, so any strategic game with finitely many players and strategies must have a mixed equilibrium, a mixed Nash equilibrium. Okay. All right. Okay. Okay. And the idea is using Brouwer's fixed point theorem. I won't say too much about Brouwer's fixed point theorem. It basically says that if you take a continuous function, so any mapping, any continuous function with the same domain and codomain, has a fixed point. So it's a fixed point, meaning that it doesn't change. And so it does not change. So you map from one set to the other, it does not change. Okay. All right. Okay. And the way the proof of Nash's theorem works is that it will take any mixed strategy and try to map it to something that perhaps have a higher utility than before. Okay, so it takes any mixed strategy and try to get it, try to improve that. Okay, so idea, take any mixed strategy and map it to something better. Right, so something better means higher utility. Okay, so take any mixed strategy and take that as our input of our function. And as our output of the function, we'll try to get something that is better than before. Okay. All right. All right. Okay. All right. So this is how we have the example with the rock, paper, scissors. I don't think I will go through the example again, but maybe I'll come back to it a little bit later. But the way we do this is through another function, right? So this is the function that records improvement, right? So improvement function. All right. All right. So for this improvement function, it looks like this. Okay. Okay. So for a player S, player I with a pure strategy S, right? So this is player I. And this is pure strategy S. And the input here is any strategy profile. Okay, so given a strategy profile, this function will tell you, well, can you get a better strategy? Can you get a better utility by switching to this pure strategy? Okay, all right, so is that right? Okay, so maximum of 0. Well, no, this is the improvement function. So this is the, suppose I switch the function. Suppose I switch my strategy to this pure strategy. Right? What will be the improvement for me? Okay, right. So this is what happens when we switch to S. And this is the original utility. Right, so this is the improvement function in the sense that it records how much can we improve by switching to a pure strategy. Okay. All right. So now here's the question, why do we care only about the improvements over pure strategies, right? So why only pure strategies are involved? Right, so when we think, so given a strategy profile, we want to improve our current strategy. Right? So I could change my strategy to any pure strategy or any mixed strategy. Okay, but in this function here, I only care about what happens when we switch over to the pure strategies. So when I switch to a pure strategy, does my utility improve? Okay. All right. And the reason for thinking only of pure strategies here is going back to what we just said earlier, right? So in this case earlier, we can say that really, if you want to have the highest mixed strategy, it must be the same, the utility must be the same as one of the pure strategies. Okay, so the highest mixed strategy among all the strategies would be the same as one of the pure strategies. Okay, all right. So this is why we only need to consider the pure strategies when we're trying to improve our utility. Okay, so why only pure strategies are involved? Because since this, the maximum is among the pure strategies. Okay, so the maximum improvement would be among the pure strategies. Okay. It can also be in a mixed strategy, right? So if you two or more pure strategies are maximum, any way you mix them would be maximum possible. But it is definitely among one of the pure strategies. Okay. Right. So when we pick a pure strategy of maximum utility, we also pick a mixed strategy. Well, you also pick the maximum utility for a mixed strategy. Okay. And so when we pick a pure strategy of maximum utility, we also pick the maximum utility for a mixed strategy. Okay. All right. Right. Does that make sense? Hopefully. Okay. All right. All right. All right. So that's the improvement function over one possible pure strategy for one possible player. Okay. But the so what we do is to do the actual function that we want to map. So we want to map a strategy to a different strategy, not just one possible strategy. We are going to look at the ways that we can improve, right? So for player I, playing say xi, so playing xi, we would add more probability to strategies that could improve the utility. Okay, so we will add more probability to, we will probably add more probability to strategies that could improve the utility of that player, right? Okay, right. So that is yeah, so that is how we got so that is how we say we would change xsi. Right, so we change the probability that we play the strategy S we will add to it the possible improvement over choosing probability of S, choosing strategy S, right? Okay, right. So this is the original probability that we assign to the strategy S. We will assign more to it if I can increase more by switching to that as a pure strategy. Okay. So for each individual strategy of the player I, we will increase it if it helps us. Okay. All right. All right. So we'll do this for all pure strategy S of I. So we'll do this for all the pure strategy S for I. Okay. But there's a problem with this, because if you add more to your probability, then you no longer have a sum of 1 for the overall probability for player I, right? So we need to normalize it to get total probability 1. Okay. Right. So the way we do that is say, well, we add this much for every single strategy. So we add this much. So just divide 1 plus this much. Right? So we'll just divide 1 plus what we have added. Okay, so which is the sum over all strategies, this improvement function. Okay, so that's how we get the new strategy based on the improvement function, right? So you take your original strategy, you try to improve something to it and make that better. Okay, and when we do that, we need to normalize it so that our probability still sums to 1. Okay. Okay. All right. Okay, well, so there was a question about why do we want to do this, right? So why do we want to switch this to something that is still a mixed probability? If we know that we can improve by switching to S, why don't we just switch entirely to a pure strategy S? Okay. Well, so that's a little bit harder to explain, but the idea is if you do that every single time, then you're going to just end up with pure strategies all the time. And as we know, there are games with no pure strategy in equilibrium, right? So it would just, if you do that for every player, they would just keep on going in circles, going around and around, and not getting a Nash equilibrium, right? So why don't we simply switch to a pure strategy instead of needing to refine our mixed strategy. Okay, and the idea is that we might not have a pure strategy in Nash equilibrium. We may need to mix it. Okay. Okay. So the idea the idea is if you look back at the rock paper scissors example, if I can bring that up, rock paper scissors example, right? So if player one plays rock and player two plays paper, we might say, well, why doesn't player one just simply move to scissors instead? Okay. Well, the thing is, we need to try to compromise between the two players. If you switch to scissors, then player two might switch to rock, and then player one might switch to paper. And it will just cycle around and around, and it will never get there. Okay, so that's why we kind of want to have some mix so we can improve. So from rock, we can improve by pushing towards paper or scissors, more so towards scissors than paper, right? So that's why we push towards scissors a little bit more than papers for player one, when it's rock here and paper here. Okay. All right. Okay. All right. So that is the basic idea about the function that is used in the proof of Nash's theorem. Right, so you try to improve every player's strategies as long as it does improve the utility. Okay, and this function. So the main idea is we map. We are guaranteed. I can't spell. Okay, we are guaranteed that are improved. That each player's utility improves. Well, not necessarily improves, but it's no worse than before by applying this function. Right, so we take this function that maps strategy to strategy. Every time so we map it, we apply the function because it gives me something better than before. Okay, so that is a function that improves our strategy. Okay. All right. Good. Any questions so far?
I have a question about that.
Yeah.
So because like each time we apply it for one player, like it gets a bit closer, like a bit more mixed or something. Does that mean we have to like go back and forth to apply it for each player? Because like if we just applied it for one player like over and over, we get closer to a pure strategy, right?
So we're applying to every player all at the same time, right? So every player will take their strategy. We'll look at the strategy for every player, and every player will improve them simultaneously. Okay, so then everybody will improve, and the idea I give you in class is that it seems that we will just improve. We will apply this function repeatedly until we converge onto a solution. Okay. But the way the proof of the theorem works is a little bit different. Okay. So how the proof works. Okay. So our interpretation is that we repeatedly apply the function to all players until it converges. And this will probably take infinitely many times to converge, but this is one way of visualizing it. This makes it one possible way of visualizing how this proof works. Okay, but in reality, though, the proof only applies the function once. Okay, so the proof only applies the function once. Okay, so what it does is it will apply the function once, and it will let the Brouwer's fixed point theorem to find that conversion point for us immediately, right? Okay. So, so one way to imagine this, so we would imagine this as some kind of as a vector field. Do you know what a vector field is? Have you seen a vector field? Hopefully. So imagine, say this is player one, and this is player two. Okay. Okay. So what we do is we will imagine that we are applying to each mixed strategy to get a direction for which it improves. Oh, I'm running out of space here. Okay, so we're applying to each mixed strategy to get direction for which it improves. Right? So if I have, say, rock, paper, scissors, for example. Okay. Right, so this is going to be a little bit terrible. So we have, if player two plays paper, so if player two plays paper, there, and player one plays rock in the initial one. Basically, what we're saying here is player two will just not change. Right? Is that the right idea? Right, so let's just imagine player two plays paper, and let's see what happens to player one. Okay, right. So player one will tend towards getting towards scissors, right? So player one will want to play scissors. So essentially, if you're playing scissors, then you would not change. But if you're playing everything else, you will be pointing more towards scissors. Okay. This is not really the best. Okay, so imagine a vector field like this, and everything will try to tend towards scissors. Okay. Okay. This is not really a good illustration, but yeah. So essentially, what we're doing is trying to find a vector field, something like this. To do this justice, I actually need to have something that is in 6 dimensions, because there are technically actually 6 strategies I need to play with. But you're imagining that you're you're imagining that for each of the strategy profile, you're trying to move towards something that's better. So they're pointing towards that direction. And Brouwer's fixed point theorem just tells me that if you have this continuous set of directions among all the strategies, then it will eventually, it should give you something where it doesn't change. Okay. I think a better illustration is probably with only 2 strategies, right? So probably something with 2 strategies is a better illustration. So maybe I'll just erase this and pretend that this didn't happen. Right, okay, so here, a new something a little bit different, right? So if you remember the Bach or Stravinsky, is that, no, the matching pennies. Let's do matching pennies. Okay, what was the rules of matching pennies? I don't remember. So something about heads, tail, heads, tail. Right, so something like that. Okay, so let's say this is player 1 and this is player 2. Okay, so there are 2 strategies each, so it's basically a linear thing for each. So you can imagine that it is a square. Okay, all right, so let me just remind myself how matching pennies work. Was it, let's see, I think it was +1 if for player one. They win if they, yeah, for player one is 1 if they match, -1 if not. And for player two, 1 if no match, and -1 if you match. Okay, all right. Okay, so if we have, say, HH here, right, so it's 2 heads, so it's match for player one, but player two doesn't like that. So player two wants to move towards tails. Okay, all right. And then something like this will give you that, like that, like that. Okay, okay. And what you will find here is once you start looking at some mixed strategies, it will try to swerve something like this in terms of the vector fields. Okay, so this is a very very strange thing. All right, so if you look at the vectors from each of the mixed strategies, they will point somehow in a swirly fashion and leading to a mixed Nash equilibrium at the very center. Okay, so I'm basically applying the function once, looking at all the strategies profiles and see how the function changes how the function improves the strategy, right? So if it's heads and heads, it will move towards that direction. Heads and tails will move towards that direction. Okay, if it's mixed, then there's a mixed direction, but they will all swerve towards the center here, right? And that is our fixed point. Okay. Okay, this kind of vector field is continuous, so fixed point exists by the Brouwer's fixed point theorem. Okay, not sure if that helps with visualizing, but so this is how the proof would work, right? So you're looking at all the mixed strategy profiles and try to say which direction does it point towards. And because of the way it's continuous, of the way the directions are continuous, Brouwer's fixed point theorem will tell me that there is one point, at least one point, that is fixed, right? So that is our mixed Nash equilibrium. All right. All right. So that's a very high concept, high level description of how Nash's theorem works. All right. So that's all. That's what I have. So do you have any questions? Well, hopefully that was kind of coherent, and hopefully you understand how things works a little bit better. Okay. If you don't have any questions, then I guess we're done for today. All right. So thank you very much for coming, and hopefully you have a great week, and I'll see you again on Monday. I should start recording.